Today we're going to talk about conic sections using calculus. So conic sections, actually in calculus. We're not going to have any calculus in this discussion, just the way conic sections are used a little bit and how they're defined. So conic sections are basically things like lines, x's, you can have an x that's a conic section, circles, parabolas, ellipses, hyperbolas, and I guess if you want to, you can say points. So conic sections. The reason that they're called conic sections is because a true cone in 3 dimensions looks something like this. My artwork isn't all that great. And if you slice it with a plane, kind of like that, you're going to get a cross section. So if I do that, like this one, if I would have done that, I would have had a hyperbola because it would be circular, kind of rounded, not circular, but rounded on top and bottom. So it looked kind of like that. I could run a plane right through here, and obviously I would have a point, run it through here, and I'd have a circle. If I tilt it at all, I'm going to have an ellipse. So there are some of the items. You can see the X, you can see single lines there. So anyway, those are all conic sections. And we're going to focus on 3. The first one is parabola. And if you've had college algebra anytime in the recent past, you probably are sick of parabolas. Parabolas tend to be written like this in college algebra. Y equals, then they usually say something like a times and then x minus h squared plus k. Pretty common way to do it. This opens up or down, all is well. Well, that is the algebra method, and it works great, but it doesn't give us all the things that you and I need. So what we're going to use is a little bit of a twist on that. We're going to use something like this, x minus h squared. Notice the h is still the same, but it's equal to 4p times y minus k. Now the k is the same too because you could have subtracted k from both sides. The difference is right here, and the fact that it's in front of the single power item. So that's pretty important. This one has x squared, so it's got a vertical axis. Okay, axis of symmetry, vertical axis of symmetry. Now, if I want to have a horizontal axis of symmetry, I go like this. I've got y minus k squared is equal to 4p times x minus h. This one has a horizontal axis of symmetry, which is great and fine. It is not a function, but that's okay. Not a function of x anyway. So there is that. We have a couple of important things. One is that here the vertex is going to be written as HK, just like before. Right here, same thing, okay? Vertex at HK. And then there is a focal point. Now, focal point is a place, let me try to visualize this for you. So let's say we've got a parabola. Focal point somewhere right in here. It's a point, and this is only one interpretation, but it's a point that if I have like a light ray that comes in here, it'll bounce off and go to that focus. Kind of like that. Okay, so that is one definition of that. A parabolic mirror focuses all the rays on one spot and creates a whole lot of light. So it's kind of intriguing. But the focal point for this one is at h, comma, k plus p. And the focal point for this one is at h plus p, comma, k. So you add that p value and you go in the vertical direction if it's got a vertical axis of symmetry. You go in the horizontal or the x direction if it's got a horizontal axis of symmetry. So the focus is p units from the vertex. And we've got to keep that in mind. So that is how we're going to deal with a parabola. Now, second one that we're going to talk about is an ellipse. You may have worked on ellipses before, maybe not, but the basic format for an ellipse is like this. It is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. Now, a and b, or a squared and b squared, can be split or put in the opposite locations. It depends on how you want to do this. So we've got to deal with a. So a has got to be equal to the semi-major axis. It's actually a length if you take a positive value for a. Now, what is semi-major? Well, it's half of the major axis. Semi is half, and major is the long axis. That's all it means. So half of the longer axis. And there is a value called c, and c is related to this in terms of this. C squared is equal to a squared minus b squared, and c is equal to the distance from the center to the focus. Now, there are two focal points in an ellipse. So let me give you a really bad graph, but maybe an idea here. So here's an ellipse. It's got a focal point here and here. Now, the reason I know that is the major axis is the longer axis, so it's this one. So that's the major axis. And here's the center. That's at HK, by the way, just like circles, just like all kinds of things. Here is the value C. Okay? And the semi-major axis length is to here, that is A. This one is actually B. All right? So I've got a horizontal major axis on this one, and it's just whichever value underneath either x squared or y squared, whichever one of those is bigger. So we'll work on that a little bit more as this goes on. The next one I want to talk about is a hyperbola. Hyperbola. Oh, by the way, let me get back to this. C and A, in this case, are related in that C over A is equal to E, and it's not the number E, the 2.718, but E is equal to what's called eccentricity. How eccentric is this, actually? And you could take that to mean a lot of things, and it kind of works well. So ellipses that are pretty round have eccentricities that are close to 1. And if they're close to 0, then they are super eccentric or very long, okay? So in an ellipse, 0 is less than e is less than 1. So it's got to have an eccentricity of less than 1. Okay, so, and notice we're using all positive values for a and b and c here. So hyperbola. A hyperbola's basic formula is this: x minus h squared over a squared minus y minus k squared over b squared equals 1. Now again, a and b can be swapped out there, and the minus sign can be in front of the x squared term instead of the y squared term also. The one that's positive directs how this thing opens. So hyperbolas look like this, or like this. This one opens in the x direction, so it looks like that one. If I had positive in front of y squared, it would open up and down. So that's the coding for that. And in this one, c squared is equal to a squared plus b squared. So it's like in the Pythagorean theorem there. A is equal to the distance from the center. So from the center, center's at HK, just like we've discussed before, the center HK to the vertex. Now there are 2 vertices. You could kind of come up with 4, but there are only 2 that have graphing parts to them. Here's a vertex and here's a vertex, or here's a vertex and there's a vertex. So it's like a vertex on a parabola. E equals c over a is the eccentricity. So E equals c over a, and it's got to be greater than 1 if you've got a hyperbola. So they're pretty eccentric as well. Okay? So those are the basic ones that we're going to work with. Now, I've got some examples that I want to deal with, and let me start with one that's relatively obvious. Maybe it's obvious if I've got the formulas. So here are some examples. I've got x minus 2 squared over 16 plus y plus 1 squared over 4 is equal to 1. This has an x item squared plus a y item squared. So since they're both plus, this one is an ellipse, and equal to 1 also. The center of this, just like you've done probably with circles and parabolas and stuff, the x value of the center is 2. The y value, negative 1. You can find that by setting this set of parentheses equal to 0 and solving. Same thing here. So the center is at 2, comma, negative 1. What we want to say the major axis is, so we've got a major axis, and it is, now this stands for a squared. So the major axis is 2 times a, because what happens is you go a units in the x direction. So a units left and right, b units up and down. So a left and right, b up and down. So if you go left and right, you get 2a. So 2 times, in this case, it's going to be 2 times the square root of 16, or 2 times 4. So we've got a major axis of 8. We need to find our c value. Our c value comes from saying that c squared is equal to the big one of these minus the smaller one. So 16 minus 4, so that's 12. So c equals the square root of 12, which is 4 times 3 under there, so 2 times the square root of 3. So that's the distance from the center out to the focal points. So here's what we know about this. It opens, well, it doesn't open. It is longer in the horizontal direction than it is in the vertical. It's got a center of 2, negative 1. Major axis is 8 units long. The c value is 2 square roots of 3. That's the distance from the center out to the focal point. And the eccentricity, if you want that, is equal to c, which is 2 square roots of 3, and divided by a. A is 4, because this is a squared. So this is actually square root of 3 over 2, okay? Square root of 3 over 2 is in fact less than 1, so it is an ellipse in that respect as well. Let's look at another example. So here's another one. Call that one number 2. This one is x minus 6 squared minus 2 times y plus 7 is equal to 0. Now if you notice, not everything has a square here. Only the x part has a square. So that immediately tells me that of these three, this one has to be a parabola. And the x portion is squared, so it's got a vertical axis of symmetry. Let me write it the way that it's written up here in my formula. Got it kind of hidden from you, don't I? Right there. So it's right here. Here's what we've got. We've got x minus 6 squared, and then I'm going to move this stuff over, so I've got 2 times y plus 7. I just changed the sign there. So here is x minus h squared equals 4p y minus k to fit the pattern. So hk, that's the vertex, is at 6, negative 7. P is equal to 1/2. 4 times 1/2 is 2. So we've got to go from the vertex into the parabola 1/2 unit to get to the focal point. So we could say that the focal point, the focus, there's only one here, the focus is at h, which is 6. And k plus p is minus 7 plus 1/2. So this is 6 and minus 6.5. You could call that 13/2 if you want. So this thing opens up. I know it opens up from previous experience in algebra, but also the fact that it always opens kind of around its focal point. And the focal point is higher up than the vertex. So there's an example of a parabola. Now let me change pages just a little bit so that we can get some more examples going. The next example that I have is this one. So this is number 3. And I'm going to put x squared minus 2x minus 4y minus 7 equals 0. I've got to identify that. Well, again, it's like the previous one. X is squared and y is not. So again, I've got a parabola. So I've got to be able to recognize those. If I write this in the format that we've got, the x is squared, so I've got to make it look like this. X minus h squared is equal to 4p y minus k. Then right here, I am going to have to complete the square. So let me take this stuff and move it over. That gives me x squared minus 2x is equal to 4y plus 7. If I take this, divide by 2, because this was a 1, so I didn't have to do anything special, but take minus 2, divide it by 2. So minus 2 divided by 2 is equal to negative 1. Take negative 1 and square it, you get positive 1. Add 1 to both sides. So plus 1, plus 1. Now we've got this. We've got x minus 1 squared. And then over here we've got 4y plus 8. So 4y plus 8. I have to factor the coefficient of y to make it look like this. So this is going to be 4 times what? It's going to be y plus 2. So here we have a vertex at 1, negative 2. It's got a vertical axis of symmetry. And the p-value, 4p is equal to 4, so p equals 1. So the focal point or the focus is at the value 1 comma k plus p. K is minus 2, so minus 2 plus 1. So it is at 1 comma negative 1. So there's your focus. Now, another example. This is number 4. X squared plus 10y squared minus 6x plus 20y plus 18 equals 0. This one has x squared and it has y squared, so I do not have a parabola. I think that I have an ellipse, but I am not positive until I complete the square. I can't make that decision yet. What I am going to do is I'm going to group the x's together, I'm going to group the y's together, and then I'm going to throw the constant over to the other side. So my process for completing the square goes like this. I'm going to do those two together, then I'm going to give myself some space. I'm going to do these two together, and the 18 becomes minus 18 over here. This one, to complete the square, we take minus 6 divided by 2, that's equal to negative 3. Then we square it, and that gives us 9. So plus 9. I've got to add 9 to this side. So this one becomes x minus 3 squared. Now this one, I've got to factor the 10 out. So I'm going to do that. I've got y squared plus 2y. So I take 2y. I don't need the y. I take 2, divide it by 2, gives me 1. I've got to square 1. So 1 squared is 1. I add 1 here, and I add 1 here. Well, what I really did, actually I don't add it there, I add it here. Excuse me. What I really added was 10. So I need to add 10 over here. There's what we have at this point. Now, let's check this thing out. This is plus 10 times y plus 1 squared. And this one over here is equal to minus 18 plus 9. That's minus 9 plus 10 is 1. All right? In order to make this fit the format, we've got to have 1 on this side, and we've got to get rid of this 10. How do you do that? Well, you've seen this probably with some kind of limit problems and other things, series maybe. What you have to do is you have to take the reciprocal and stick it in the denominator. So we're going to have this. We're going to have x minus 3 squared plus y plus 1 squared over 1 over 10. I know that looks terrible, but that's exactly what you need to do. And it's equal to 1. So this stuff is over 1. This is over 1/10. Now, how do we figure it out? Well, both of these are positive, so it is an ellipse. The vertex, or not the vertex, the center is at 3, -1. 3, -1. The major axis is the bigger one of these. Well, it's x, so the major axis is the one that's in the direction of x. So a squared equals 1, b squared equals 1/10. So if we want to find the eccentricity, we've got c squared is equal to the bigger one minus the smaller one, which is 9/10. So c equals the square root of 9, which is 3, over the square root of 10. 3 over the square root of 3, or over the square root of 10. So we've got 3 divided by a little bit more than 3. This isn't really too far from 1, but it's a little bit more, or a little bit less than 1. So there is the eccentricity. This thing opens in a horizontal direction. not really opens, it's wider in the horizontal direction. The minor axis is 1/10. Now, my last example, let's look at this one. This one has, this one I'm going to call number 5, and it has this. It's got y squared minus 16x squared plus 64x minus 208 equals 0. This looks initially like a hyperbola, but I don't know that for sure yet. I need to complete the square because I've got x's and x squareds. Y squared, don't have to complete the square on that. That one's nice because it's the only y in the whole problem. This one, though, I've got a factor out of 16, so I might as well start out by doing that. Got x squared. 64 divided by minus 16 is minus 4x. Close this up. Move this over here, so I've got equals 208. Now, to complete the square, since I factored that leading coefficient out, I take negative 4, divide by 2, gives me negative 2. Square negative 2, I get plus 4. And what I really did was I subtracted 64 from my problem. So I need to subtract 64 from this one. So now I have this one, I've got y squared, which you could write as y minus 0 squared if it helps, minus 16 times x, this is minus 2 squared. This is 208 minus 64, which is 144. Nice number. We have to divide by 144, so this is 1. So divide by 144, divide by 144, divide by 144, okay? And so, you know, we've got some situations here. We've got 16 over 144. 144 divided by 16 is 9. So we're going to cancel this and give ourselves a 9. This is 1. So here's what we have. We've got y minus 0 squared, and you don't have to write the 0 part if you don't want to, for 144 minus, and we've got x minus 2 squared over 9 equals 1. Subtraction in between, we've got a hyperbola. Which direction does it open? Well, the positive one is the y1, so it opens up and down because y is the positive one. The center is at 0, 2. The major axis, if you want, is 12, and the minor is 3. So if we want to deal with, like, where's the focal point, or where are the focal points, there are 2 of them here, we could say that c squared is equal to a squared plus b squared. So it's equal to 153. So c equals the square root of 153, which, you know, not a really great number. Not a perfect square, certainly. Notice I'm only using positives here. If I need the eccentricity, E is equal to A over C, so I'd have 12 over the square root of 153. I said that wrong, didn't I? It's C over A. Excuse me here. Let me fix that. C is square root of 153 over A, and that is greater than 1. So hyperbolas are quite eccentric, so to speak. Now, something else that you might notice